Good afternoon, everybody. Welcome to the seminar series. I'm Shiquan. I'm from the User Assistant Group at NICS. Today, I'm going to talk about the compiling basis for HPC. So let's start from what we need from getting a source code to an executable ready to run on the HPC system. Of course, this also applies to any desktop, any scientific computing platform you are working on. So generally, it includes the three steps. First, of course, you need to edit your source code. For example, let's say you edit an Hello World program. And then you need to compile your code, which usually will generate the object file. Let's say you compile the object file hello-world.o, and then finally you need to link your object file to an executable. Let's say you name it as hello world. Usually by default, if you do not specify your executable name, the executable will be generated by default, named it as a.out. So let's use a C++ program as an example. When you, at the step of edit the source code, usually you will have a main, at least you need to have a main program. Sometimes we call it drivers. Usually you put it in a file ended with .cpp. And then you might have a bunch of header files, and you will put it in a bunch of files named it as something .h. And these files, usually they are required at the compile times. Also, you may have some functions, some subroutines files, and usually this file will be compiled into a library. So, and in some cases, if these functions or subroutines are from external, and then they may just require at the link time. Usually, you will put this file in the .h file or in the .cpp files, up to your choice. So after you edit a bunch of source code files, then you will try to compile them to the object file. So compared to follow the previous step, usually your main program, for example, if I name it driver.cp, will be compiled to a driver.o files. During the compilation, the compiler will help you to check the header files. So the compiler will try to find all the all the .h file if they're in place. If they are not in place, they will become a fatal error, and your compilation will just fail. And during the compile time, your files include all the other functions, subroutine, class. They will be compiled, usually they will be compiled into a bunch of .o file. And then we have the command ar, which means archive. You can use the r command to bundle them into a .a file. Usually, this is what you will see in the library, in the folder of the library files. You will see a lot of .a files. This also, the .a file represents the static library files. Sometimes if the file is compiled into a dynamic library, then usually it will be named as lib.so, for example. It will end as with the .so. And then after you compile your object files, you will need to link to an executable. And this moment, you will link your drivers your libraries together. For example, you will link your drivers.o and your lib.a to the executable. You can name your executable as any names as you want, or it may by default be generated as a.out. So your driver first become the driver.o, and then your driver.o link with the libraries will become the executable. So here is a simple example. We can use the command line command to compile a very simple code. So for example, I have a hello world program. It's a C++ program. So on the slides, I also cat my hw.cpp files, which is my code. As you can see, it's really simple, but it includes most of the components we need to compile a code. For example, it starts from include some header files. So, and then it's the main program. And for example, for the cout functions, it's included in the libraries. You need to include your header files properly before you can use it. That's why we need the header files. And then we try to compile it. We use the GNU compiler. And inside the GNU compiler, the corresponding C++ compiler is called G++. And then in this simple case, the compiling command line can be as simple as just G++ followed by your source code name. So after you execute the G++ hello world.cpp, then you will, by default, you will get the executable, which is a.out. And then we execute the a.out, we get the hello world. This is a simple example explaining how the combination works. In the later part of this presentation, you will see a more complicated procedure to compile your application. So nowadays, if we really be on the frontier of the computational science research, usually we need to use a supercomputer, which has a large number of processors, a large number of nodes. So in this case, it's not enough to just compile your code serially, which can only be run on one core or one node. This is obviously not a very good use of the resources of the high performance computing. So we need to compile some MPI code. So then we can use hundreds of thousands of code to help us to finish our calculation. So in the next step, let's see what we need for MPI compiler, what we need to compile our MPI code. We still use the C++ as example. So basically, compared to the previous example, for that G++ compiler, now we have a MPI compiler. Let's say it is called MPI CXX. According to different MPI implementation, they may have different names for their C++ compiler, for their MPI C++ compiler. But the MPI CXX is a very commonly used name for the MPI compiler for the C++ program. So when you are on a supercomputer, before you want to use an MPI compiler, you need to check the several things listed below. For example, if we use the C+ language as example, probably you want to find the header file of your MPI implementation, because we know that the MPI is entering the code as a library. You can, if you want to use the MPI library properly, you need to offer the code the right header files, also the right subroutine code, such as MPI init, MPI rank, MPI size, you name it. So before we can do that, we need to check is all these files ready, and at least several points you need to check for your inside your MPI package. You need to check the MPI header files, MPI.h, and you need to check your actual MPI library where it is. Usually, if we call libmpi.a, again that depends on different MPI implementation. The name may have slightly different, but by common sense, usually you can find them at the same place or the similar place. And then, of course, the executable for the compiler itself, which is usually called MPI-CXX. Also, there's another executable you need to pay attention to. It's called the MPI launcher. Because after you compile your code, when you get your executable, if you want to run your executable across the nodes, you cannot just type in your executable. It won't work. It will just still run on one core or one node, and probably it will throw you a bunch of error message because you cannot execute the MPI command correctly. If you want to run an MPI executable successfully, besides the executable itself, you also need another executable, which we may call it MPI launcher. Usually, the MPI launcher will be called MPI run, or in some cases, it will be called MPI exec, MPI exec. And in the later part of this presentation, you will see there's also other names. If it's under the crate wrapper on the crate machine, it may be called AP run or some other different type of names. So here, I will use an example to show you how to check your MPI package. Let's see the Open MPI library on the Kinnan machine as example. So now I will switch to a terminal and show you how to check your MPI package. So I log in first I log into the Exit single sign-on hub, and then I go to the Kinnan machine. So you can see my terminal, right? Okay. So for example, you are on a supercomputer, you are new to this supercomputer. What should you do? Usually, we can start from the command module list. This will show you a bunch of modules already loaded by default for you. Usually, it will include the program environment, the default compilers, and probably the default MPI implementation, and the default numerical library. In this case, is the MKL. So let's see how can we check the MPI library. So you can start by the command module show. And then we will see what's inside the MPI implementation on this machine. So basically, it starts from here. If you check the MPI package, usually it will include the bin folder, which will have all the executables inside. You will have the include folders, which will have all the necessary .h files inside. You will have the lib folder, which will contain all the library files. So let's check the bin first. Bin has a bunch of executable. Most of them you will probably never use it, or it will be only used in a very special situation. So, but there were several very commonly used, very important executable, as you can see. For example, here the MPI C++. By the name, you can understand that this will be a MPI compiler for C++ language, and you will have MPI CC. It's pretty easy to guess. This is for the C language itself. Also, you have for example, you have the MPI CXX, which is also for the C++ language, and then you have a bunch of Fortran compiler, for example, MPI F77 or MPI F90. And besides that, if you can find that you have another type of executable, such as MPI run or MPI exec, MPI exit. This is the MPI launcher I mentioned to you before. So after we check the MPI folders of the bin folders under the MPI implementation, we can check another folder, such as the include folder. Here you can see some of the .h files. This .h file is what the MPI needed as the header files inside the program. There are two most commonly used files. One is the MPI.h, which is usually used in the C and C++ language. The other one is MPIF.h, which is used by the Fortran language. So after we check the include folder, we can go ahead and check the lib folder. As you can see a lot of libraries files here. The most common used one is the lib MPI.8, which is a static library for the MPI library. And you may see that it has the counterpart for the dynamic version, lib MPI.so. So basically, you can expect that if you have a .a library files in that folder for the static linking, you can also expect it may have another files with the same name but just end with .so for the dynamic linking situation. So here I showed you how to check your MPI compilers on the supercomputer before you go into your compiling procedure. So next, we will talk about another type of compiler, which is, we usually call it compiler wrapper. It's provided by the crate. So crate provides a convenient set of compiler wrappers commands that it should be used to compile or link the programs to be run on the compute node. So the wrapper itself will invoke the corresponding back-end compiler in the current loaded program environment correctly. Invoking the wrapper will automatically execute the following steps. So first, it will import the path for key header files like the MPIH, just as I explained in the previous slides, and other libraries correctly. Also, it will link the MPI and other fundamental header files and the library needed to be run on the crate machine. And then it will automatically include and link in the header files and library loaded via the module system. And then it will specify the correct target processor's arguments. It will provide a common interface to all compilers. And under the crate compiler wrapper, the MPI launcher command now is the AP run. So the following table lists the compiler wrappers and the corresponding back-end compilers available on the most of the supercomputer system. So, for example, for the compiler, if we, mainly we will have we will use three types of different language. One is C, C++, and Fortran. For the wrapper, the C language will be CC. For the C++ will be capital CC, and for the Fortran will be FTN. And then you can see for the Cray compiler, it will call Cray CC, Cray capital CC, Cray FTN. For the GNU, it is GCC for the C language, G++ for the C++ language, and the G Fortran. And for the Intel, it's ICC, ICPC, iFort. And for the PGI compiler, the C compiler is PGCC, for the C++ is PG capital CC, and for the Fortran is PG Fortran. So next, we will see an example of a Cray compiler wrapper case. We will use the data machine in the NICS, National Institute of Computational Science, as an example. So on the data machine, the compilers have the following options. The default compiler is the Cray compiler, and the available compiler on data are the Cray compiler by default, and also the GNU compiler and the Intel compiler. The PGI compiler and the Pascal compiler are no longer available on the data machine. So there was some common compiler options which is useful basically nearly for every applications, and we list below. Just for comparison, we also list the case in the PGI compiler, although it's not available on the data. The first common use compiler option is something called called dash fast. In the Cray situation, it's optimized by default, and for the Intel, besides dash fast, you also say dash no dash IPO, and for the GNU one, it's dash 03 and dash F fast dash math. And this is the standard optimization flag options for the compilers. It will make your code run faster, just like a magic, kind of like you may gain 50%, let's say, or up to several times faster. Run fast, the code you run that fast. I just make up the number, don't quote me on that. The real situation depends on case by case. And also, for example, you have the compiler option dash P for PGI, dash HOMP for Cray, dash OpenMP for Intel, dash F OpenMP for GNU. That is for enable the OpenMP thread support. So you can run your code in application in thread. Also, for example, for the dash M fix dash M free for the PGI, dash F fix dash F free for Cray, dash fixed dash free for Intel, or dash F fix dash form dash F free dash form for GNU. This is the options, compiler options to instruct the compiler process the Fortran source code as fixed or free format. Besides these options, there was a lot of other options you can exploit under the compilers. I did not list them here. So next, I will talk about using the dynamic linking on the data. So when you try to link your code, your object files to an executable, you have two ways to accomplish this task. You can link it statically, or you can link it dynamically. So let's see what we need to link it dynamically on data. It's a little bit, it needs a little bit more work compared to the static linking. So some applications requires the use of dynamic linking and share libraries on the compute nodes. Example of these including the software from third-party vendors and popular applications such as Python or OpenFOAM. Data fully support the use of the share library and the dynamic linking on the compute nodes. All Craze provided software on Data were also built with share library support and can be used by dynamically linked application. I can go to full screen again. So here is the example. The user can link the application dynamically by either setting the environment variable capital Quapier underscore link underscore type to dynamic, or by adding the dash dynamic flag during linking. The following shows some examples on building a dynamic link application and share library. So if you follow the first approach, you can say export the create type underscore link underscore type equal to dynamic, and then you can execute your compile command line compile command. And then the same example as above, you can use a linker flag, such as you can say cc and then say dash dynamic as a flag, and then dash o hello.c. Then the code can be compiled and dynamic link on the data. The same procedure applied to FTN and the CC to build the Fortran and the C++ code with dynamic linking. So for the examples on data, you may find more information for the data machine under the following link. As we can see here. So there's a detailed documentation about different aspects of the machines. And we can see that there's a section talking about the compiling. And there's a bunch of information here. If you are interested, it's welcome to go to the website and check them out. Next, we will talk about the make files. Usually, when you work on the supercomputer, your code or your application will be pretty complicated. It's unable to manage it by hand. The compiling procedure will be so complicated. You cannot just finish them by command line command one by one. So in this case, you need to use a utility which called make. And in order to use make, you need to edit your make files. You can use the make file to manage the dependence of your code or application automatically. So the common structure of a make file is for each section, you will have 3 parts. The first part is called target. It will appear on the first line on the left side of the column, which means that this is the target eventually you want to have. And on the right side of the column, it's called component, or it's called dependence, which is telling the makefile system, the make system, that in order to have your target, in order to have what you have on the left-hand side of the column, first you need to have what's list on the right side, what is list under the component. So if any of the component is not ready on the right side of your column, then the makefile will jump to the section corresponding to that component and try to work out that component first before the makefile comes back to take care of your target. And if all the components are ready for making the target, then the makefile will execute the third part, which is the command below the first line. And we need to especially pay attention that for this part, each line is started with a tab. Depends on the implementation on your computer, in your editor, it may appear as 4 empty space or 8 empty space, but it must be a tab. It will never work if you put 4 space there, 8 space there, even they look the same width as the tab, they will always fail. For this part, for the command part, you always need to start with a tab. In this part, you can put in multiple commands just one by one. And this is one of the smallest block you have to work on for each makefile. And then you may have a lot of blocks to take care of different programs for different functions in your makefile. So inside your makefile, you will use a lot of flags to represent what you have for your computational environment. Because pay attention that every applications, every code is developed under a certain computational platform. The developers, he may has a very different computational platform compared to yours. He may using the Intel compiler, he may using OpenMP as the MPI implementation, and you may use the GNU compiler, you use the MPI-CH as the MPI implementation. So, but most of the time, if a code is mutual, if a code is a successful code, it should be able to run on different platforms. So in this case, the makefile should have the flexibility that which can be customized for different computational platform. So in this case, one of the most important procedure is you will represent all these command or parameters by flags. So in this case, you only need to change one place for the definition of the flag, and then your code can completely be run on the other platform. That usually the information about the value of all these flags will be stored in another files associated with the makefile, which usually called make.inc. The inc stands for include. So there, in this slides, I list several common use flags, such as FC means Fortune compiler, and I give an example here. You can assign your Fortune compiler as the MPI F90 if the MPI F90 is the MPI compilers on your environment. And for the capital CC, here I associate the MPI CC to it, which is a C compiler. And for example, you have the FC flags. You can understand this name as the Fortune compiler flags. And for example, if you want to optimize your code, you can use -03. It's a pretty high optimization level. The CC flag is for the C program. And then later you can see that the other flags may also be defined by the flag you defined previously, such as you can define your FC loader flag as the same as the FC2. And then later, for example, you can see there's a flag I call blast lib. The blast is the is a very common use numerical library. And here, for example, if I want to use the brush subroutine in the code, and then I just call it in the code, and I don't care where my brush library comes from. It depends on what you have in your computer, in your supercomputer. So, for example, here I offer an example where I use the MKL library to provide the brush subroutine. So follow the -L options is the path to the MKL library. And there's several other flags such as -MKL, -LM, which is the compiler flag points to the right compiler right library. And for example, I may also need the LAPACK lib flag, and sometimes the lab flag already be taken care by the MKL library, so probably I can leave it empty. It still will be okay. And later you see, I will have another flag called libs, which will include all the separate library I defined before. Okay, so this will be, now we will go into the last part of my presentation. Here I will demonstrate a realistic example of compiling a view application. Here I choose the scale LAPACK as the example. The scale LAPACK is a linear algebra library which is widely used in so many scientific applications. So now I will try to compile the scale LAPACK and test driver using the makefile. So there are several steps. For example, you can edit your own drivers. Here, I will just use the example provided inside the package as the example. And then you can go to the following website to check how to use this library. So, for example, under this website, it offers a lot of detailed information of how to call the subroutine, how to find the function you need here. So it's this website is pretty useful for the scale LAPACK. Similar, if you have another application, you have another libraries, you may go to their main page to check out all the detailed information you need. And then we need to edit the make.inc to customize the compiling process to our computational platform. Here, I will use two examples. One is the data at NIX, which is a Cray machine, and then I will demonstrate how to use the Cray compiler wrapper to take care of this. And the second one, I will compile the package on the Keenan machine, where I will use the Intel compiler to show you how to compile it via Intel compiler. And the scale LAPACK package itself, it also depends on the BLAS and the LAPACK libraries. So I will show you how we take care of the dependence on during the compilation. So let's go to the data first, which I will show you for the crate case. So here I already extract the scale LAPACK package from a tarball under the scale LAPACK folder. And as I told you before, the scale LAPACK also depends on the LAPACK and the BLAS library. So I already installed the LAPACK library at the same place. So now let's go into the scale LAPACK folder. Here you can see that the make.inc file, here the name is a little bit different, means scale LAPACK make.inc, SL for short, SL make for short. So let's edit this file first. So as you can see here, so the section I want you to pay attention is this section. It asks you to define a bunch of flags, which will make the compilation customized to your computational platform. It starts from the FC, which means the Fortune compiler. So here I put in FTN. So kind of if I ask you a question now, what is the compiler I'm using here? What am I doing here? So I hope you know your answer. The answer is now we are using the Cray compiler. We are using the Cray wrapper on the machine. So the Fortune compiler will be FTN. The FTN is the Cray wrapper. It will take care of the MPI library. So actually, this FTN will represent an MPI compiler. And we use the CC for the C language. The CC is the Cray wrapper for the C language. So basically, this is all we need to change in this section. We assign the FTN to the Fortune compiler on our Cray machine. We assign the CC to the C compiler on our Cray machine. In the later part of the make.inc, they will ask us how to deal with the dependence of the BLAS library and the LAPACK library. And for the BLAS library, I leave it empty. That's because in the current version of the LAPACK, it will automatically take care of the BLAS library. So if I compile a LAPACK library, I also get the BLAS library. And for the LAPACK library, as I showed you before, I already compiled these files. I already compiled this application under the same directory. So here I just offer an absolute path for the LAPACK library. And then, for example, for this libs flag, it will include all the libraries. Here is the LAPACK and the BLAS. So here we can start a compilation. Before we start, let's clean it a little bit. I want this go successfully several times before the presentation. I hope it won't give me any surprise at this time. So now I just type in make. And actually this will take a pretty long time. And I will spend a few more minutes with you to monitor this make procedure. As you can see you call the CC, the compiler, the Cray compiler wrapper to compile the code. And later you will see the FTN or something. So this is what will happen on the Cray machine. Sometimes of course, sometimes you run into a bunch of warning, but the code can still be compiled correctly. So let's ignore the warning at this moment. So as you can see, it's called the CC compiler for the C language, and later you will see a bunch of FTN command. So I will let this running for a while. Also, I want to point out is after you compile a lot of .o file, object files, you can use there's a command say AR space CR, which means AR means archive, CR means create. Then you will create a library file. Here is lib scalarpack.a to hold all your object files. So now you can see there's a bunch of ftn command compiling a bunch of Fortran program. So I will leave this Windows running for a while to show for the compiling process of scalarpack on a Cray machine. Next, I will show you another example. I will compile the same package, the scalarpack, on Kindle, where I will use the Intel compiler. So I already logged into the Kindle machine. Somehow I lost my connection. I will restart the window. Doesn't work. So I start a new terminal. This part is still going. Kindle is somehow the Kindle is down. Somehow the Kindle is down. I tested 30 minutes ago before the presentation. So obviously we experienced some technical difficulties here. The Kindle machine is down, so I cannot connect to the server. The data one is okay. So kind of like I cannot run the compiling on the Kindle right now, but I can show you what I have in order to compile on the Kindle. So here is the similar situation. I also want to compile the scalarpack. Let's assume we are on the Kindle machine. And on the Kindle machine, I will try to use the Intel compiler. And the Intel compiler also comes with the MKL library support. So I will link I will use the MKL library to provide the BLAS and the LARPAC functions I need. So let's go inside the scalarpack folder to see how to link with the MKL library. So again, the same thing, we try to edit the make.inc file. So as you see here, now I will say FC equal to MPI F19, capital CC equal to MPI CC. So what am I doing here? So basically, if you remember what I mentioned in the previous slides, the MPI F90 is an executable provided by the MPI implementation. It will represent the parallel Fortran compiler, the MPI compiler for the Fortran. The same thing, the MPI CC is the MPI compiler for the C language. So here we want to use the Intel compiler. If I can log on the Kindle machine, I will show you that my MPI implementation is associated with the Intel program environment. It's the MPI F90 is MPI. It's a wrapper for the iFort compiler from the Intel in an MPI version. But unfortunately, I cannot log on the machine now, so I just can explain you in Word. So the key part is how we deal with the dependence, the library dependence. Again, I cannot log on the Kindle machine, so I cannot show you what we have on the Kindle machine. On the Kindle machine, we have the Intel compiler as default. So by default, the system already load the Intel module and the MKL module for you. And when the system load the module, it already take care of the library path. It already put the MKL library path inside your LD underscore library underscore path environment variable. So you can see here, if we compile on the Kindle machine, we even don't need the MKL underscore dir environment variable. We even don't need this environment variable because the path already been taken care of. The path already inside the environment variable. We only need to offer the flag we want to use, the library's name we want to use. In this case, it's -mkl-lp thread and -lm. And that's it. And we don't, and the MKL library already include the larpack function and the bus function, and we don't need to specify the other flag. Then we just put all the flag we have before for the library into the environment, into the variable libs, and then it will take care of all the dependents. Unfortunately, I cannot log on the Kindle, so I cannot show you the real compilation process. So this is the last topic I want to cover in this presentation. Thank you.